dell'Istituto e va presentando sobre Gravity for Optimized Computation.
In English, right?
Yes.
Okay. Okay, so first, thanks to the organizers for invite me to speak at this event. So in the next hour, I'm going to try to argue that in the holographic context, we can see gravity as an emergent phenomenon. More specifically, we can see gravity as emerging from optimized quantum computation in the boundary theory. So this is based on a couple of papers that I have put out in the past years. The first ones with my colleagues at University College London, and the last one that appeared this summer also with a subset of them and my PhD student, Rafael Carrasco. Okay, so the idea that gravity might be emergent is not a new idea. So the first evidence that were discussed was since the discovery of Bekenstein and Hawking from the black hole entropy and black hole thermodynamics. In particular, the fact that the entropy of a black hole scales like the area suggests that gravity is holographic and that it might be an emergent phenomenon. A few decades later, in this seminal paper by Ted Jacobson, the first proof of this statement was shown. In particular, he showed that you can see Einstein's equations as an equation of state for the spacetime. And he showed that by using thermodynamics of small local regions. This works for Einstein gravity, but with some work, you can show that this works actually for any higher curvature theory of gravity. For that, you need to upgrade this formula to the Wald formula for entropy. So this is all nice, but it begs the question about what are the underlying microscopics. So as we all know, thermodynamics is a coarse-grained description. And it's nice to ask if we might have a more fundamental derivation of Einstein's equations. So years later, this set of ideas took a new twist with the discovery of holography. In particular, with the formula for computing entanglement entropy holographically, due by Ryu and Takayanagi. So this formula, the so-called RT formula, is a very simple and nice generalization of the Bekenstein-Hawking formula for black hole entropy, but it applies for a von Neumann entropy of some CFT state. So this is nice because this is no longer a coarse-grained quantity. This is a fine-grained quantity. And via holography, then we know what is the really the microscopic description of the bulk. So this formula, along with many generalizations, have shown that gravity indeed has an information theoretic character. So there are many papers that explore how it's possible to reconstruct aspects of the bulk from entanglement. And the idea is that these RT surfaces, they probe the interior of the bulk, even though they are a bulk, a CFT quantity. So this leads to the so-called space-time entanglement paradigm. The seminal works almost now 10 years ago showed that from the first law of entanglement entropy, this is an equation that holds in the CFT description. You can show that this equation maps identically to Einstein's equations in the bulk. So this was first shown at the linearized level. And this gave rise to the so-called entanglement equals geometry paradigm. It later was shown that you can also incorporate nonlinear corrections, and you can show that this holds for theories beyond Einstein gravity. And well, at this point, I also want to mention this related work by Ted Jacobson that also derives Einstein's equations from entanglement, although this makes no reference to holography. So in his work, he derives Einstein's equation by looking at causal diamonds in the bulk, and although heuristically is very similar idea.
Juan, sorry, one question.
Yes.
This thing that you mentioned, how from the von Neumann or the entropy computation you can get the Einstein's equations. Is it a one-way map, or can you do it the other way around? Sorry if it's
Yeah, it's both ways. It's a double arrow.
Okay.
I have a question.
Yes.
Suppose there is some called shadow entanglement, or some region of the space-time that you cannot see with entanglement. So in that sense, how should I understand that implication over there?
Yes. So strictly speaking, this proof has some caveats. So one is that you can only prove it in the vacuum, and it holds for regions where the entanglement surface can reach. So vacuum or perturbations of the vacuum, that's what I meant. But that's my next point, is that in general, there are regions of the bulk that cannot be probed by these entanglement surfaces. And this led Susskind and some people to say that, well, entanglement seems not to be enough to capture all aspects of gravitational physics. So it's nice to study some other information theoretic quantities that might give us more information. So one puzzle that was raised at this point was that when you are exploring a two-sided black hole, the entanglement surface they can probe a little bit the interior of the black hole, but they don't reach arbitrarily to late times. So they fail to describe the late time growth of the wormhole inside the two-sided black hole. So this led Susskind to propose that maybe there is another quantity that can capture this growth. And he proposed that such quantity might be a computational complexity. This is a quantity that is often discussed in computer science. It essentially tells you how difficult it is to build a target state from a reference state given some set of gates or operations that you're allowed to act with. So this is kind of the intuition, the boundary intuition. In the bulk, it's fair to say that this quantity is not as well understood as, for example, entanglement entropy. At the moment, there are a couple of conjectures for what the holographic dual is. So the first two are the so-called complexity volume and the complexity action proposals. So one, what you do is to fix a Cauchy slice at the boundary, and then the CV says that complexity is equivalent to the volume of the maximal volume slice anchored at that Cauchy slice. Similarly, the action says that the complexity is equal to the action evaluated on the Wheeler-DeWitt patch anchored at that Cauchy slice. There are other more recent conjectures that go beyond these two proposals. At the moment, there is no proof that one of them is correct or not. It might be that some of them are correct in the sense that from the boundary perspective, we have a set of ambiguities in this definition, especially when you go to the continuum limit. So there is an ambiguity on defining the universal set of gates or operations that you're allowed to act with. There is an ambiguity on defining a cost function and the error, the tolerance error to achieve the target state and so on. So it might well be that some of them map to this set of ambiguities that we have at the boundary. So this raises the question is if, given that entanglement was successful in deriving some, is there a question?
Yes, sorry, Juan.
Yes.
So you mentioned, okay, these complexities, the different possible definitions. Is there any relation between these definitions and the usual entanglement entropy?
No, they are independent quantities. I would say that CV looks similar to entanglement, in the sense that entanglement is given by a minimal area surface. That's codimension 2. In the CV conjecture says that complexity is the volume, is maximal volume instead of minimal or extremal. This is a codimension 1. So it's similar, but a priori there is no connection between the two.
I see. I see. Thank you.
Yes, another question?
Oh, yeah. Hi, Juan. I had a small question. I mean, from the holographic complexity perspective, I can get that there are different geometrical interpretations in the bulk for the complexity part. However, my question was more about the boundary part. I mean, you gave this computational complexity definition. I guess that's the one that you use in the conformal field theory, the boundary, let's say. But
so this is
I'm right.
So here is the definition in the discrete in quantum mechanics, where you have a discrete gates, and in that case you just count the number of gates. But when you go to quantum field theory, it's more complicated, and there are various ambiguities. So, for example, this is what I was saying, that there is an ambiguity on defining what is the set of gates that you're allowed to act with. So there should be simple operations, but nevertheless that should allow you to explore a big portion of the Hilbert space. And there is also a cost function that tells you if you act with certain gates, then maybe there is a cost acting with some gates that are differ to acting with some other set of gates and so on.
I see. That's nice. So, but how do you define your reference state, for instance, in those cases? It's like,
yeah, that's up to you. That's up to you. So that's kind of the game is you define you just, that's an input of the program. You give a reference state, you give a set of operations, and you give a target state. So in a sense, it tells you with this set of operations, you build a quantum circuit, and complexity tells you what is the optimal or what is the shortest circuit that you can build.
Okay. Okay. Thank you.
Okay. So given the success of entanglement in asking some of these questions, is also a natural question to ask if complexity can give us something similar. And the first observation is that optimized computation is fundamental in physics. So indeed, from the principle of least action that we use in many fields, the idea is that the optimal path that solves the equation of motion is the one that reduces the costs of computing the dynamics of the system. So it might be also natural to ask if computation in the boundary gives some notion of something emergent in the bulk. It's universal enough to ask that question. And indeed, there are some preliminary ideas, both in holography and outside holography, that relates optimal computation with gravity. So there are some preliminary ideas by Susskind and Jose Barbon that basically maps the operator growth in the boundary to gravitational attraction in the bulk, from the bulk perspective. This paper by Magan and Caputa that essentially derives two-dimensional gravity from the geometry of Virasoro circuits in 2 dimensions. And there are some older ideas outside of holography that try to explain quantum computation, quantum gravity from quantum computation. So our work kind of builds on this preliminary ideas. And it can be summed up in this principle that we formulate, that gravitational equations of motion result of are a result of space-time trying to minimizing the cost of computing the dynamics. For this proof, so we state this principle, but we also prove it in certain sense. And for the proof, we use a specific notion of boundary and bulk complexity. We use in particular the so-called CV dictionary. And we show that from the first law of complexity, we're also able to derive at the linearized level, we are able to derive Einstein's equations. So that's the idea. And the outline of the rest of the talk is the following. First, I will describe more in detail what I mean by what notion of complexity I use. And for that, it's basically a notion that uses state preparation using Euclidean path integrals. And for that, it's also important the map between bulk and boundary symplectic forms. Then I will show how is the proof of linearized deriving linearized equations of motion from the first law that holds. Originally, we showed that for Einstein gravity, but in the recent paper, most recent paper, we show it for arbitrary higher curvature gravities. And in the same paper, we also explore what happens if you add bulk quantum corrections. So in that case, we show that in the CV proposal, you need to add a bulk term meaning that, so this term is codimension 1, this is codimension 0, that we interpret as a bulk complexity in a similar way as the FLM formula for quantum corrections to entanglement entropy works. And well, finally, if I have some time, I will comment on how to visualize this notion of complexity in what we call Lorentzian threads. And then I will show some conclusions. Okay, so the notion that I explain of complexity, it works for in a discretized sense. So this is what I was telling you about, that you define as an input, you give the initial state, which can be, for example, the vacuum, and you give the target state, and then you build a quantum circuit acting with some unitary operations. So in a discrete sense, you can relate complexity to the number of gates the minimal number of gates that you need to apply. However, this notion falls short when upgrading to quantum field theory. In that case, there is some advance was proposed by Nielsen almost 20 years ago. And he proposed to consider a manifold in the space of operations and define quantum circuits as just paths in this manifold. So in that sense, in that geometrization of complexity, then the complexity would be given by the length of the minimal geodesic in this auxiliary manifold. Okay, so this idea will play a role in our holographic description. It's good to have it in mind.
Juan, one question.
Yes.
So okay, sorry, Marcelo has a question, sorry. So you have a quantum circuit, and then you associate it with the geodesics, and how do I calculate that geodesic? What's the metric of that space of operations?
Yeah, so that you can propose. I will show in my definition of complexity what the metric is. It's associated to the symplectic structure, but that's something that you can propose. Your definition of complexity, you can propose what the metric is, and that might have to do with what cost functions do you assign to different operations.
Can I ask another one before Marcelo so you mentioned that you will get some linearized Einstein's equations.
Mhm.
They are linearized around what? So
Around the vacuum,
the flat space.
about ADS.
Oh, okay. Good. Right. Thank you.
Juan, sorry, one
Yes.
question. This computational circuit, let's say, in what language you can implement it? Like, could you use a programming that is available to try to construct this circuit and try to find the optimal path, or how do you
I
do
mean,
it?
for qubit systems, you can do it. You can use Mathematica to do it, but
Okay.
for a system with many degrees of freedom, is impossible to do it in practice.
Okay. Thank you.
Okay, so let's move to holography, and to understand our definition of complexity is good to review one important aspect, and is the fact that a Lorentzian spacetime in ADS-CFT can be understood as the time evolution of coherent CFT states. So the idea is using state preparation using Euclidean path integrals. So, well, for that, what is common is to, instead of considering the full Lorentzian evolution, you replace the past by some Euclidean manifold and the future by some future manifold, Euclidean manifold. And what you do is to prepare the state at this slice using this path integral. No? So this is the initial state, and then the state at this slice is prepared using this path integral with some sources. So using the extrapolate dictionary, these sources are given as boundary conditions for bulk fields. And these boundary values specify the sources that I'm turning on in this manifold. And via the Euclidean Einstein's equations, it specifies then the state at this slice. Then we can time evolve the system using the Lorentzian Einstein's equations. And then we can close the contour by adding another Euclidean manifold. So essentially, I'm using Euclidean path integrals to prepare the in and out states that are used in a Lorentzian path integral. Okay, so the way so that this process works is that I'm preparing, in general, the states that we prepare here are coherent states. Those are dual to semi-classical bulk states with a classical geometry and some quantum fields on top of that. Now, one important point is that as in classical mechanics, the set of coherent states can be described by a manifold with coordinates given by the sources. This is in fact a symplectic manifold with a given Kähler metric and some a two-form symplectic form. The symplectic form is given by the anti-symmetrized variation of the so-called Kähler potential, that is this log of lambda lambda. And well, given this metric, then it's natural to explore distances between states. So that's kind of the idea that we use. It's important that we use coherent states because the key point of coherent states is that these are a complete basis, but they have non-trivial overlaps. Okay, so that's one of the crucial points instead of using the normal energy eigenstates. So to compute complexity, we can define a cost function. The function, this is an example. We can use the kinetic energy, where this is the Kähler metric. And once we define the cost function, we minimize this cost function and compute complexity, but finding the trajectory that minimizes the cost function. So one point here is that the choice of this cost function is by no means universal. It's something that we can pick by hand. And in our work, we picked the one that they use they motivate in this work by Bellin and company. And the reason why this might be natural is because it's linear in the sources and it's additive in the sources. And those are two properties that product tensor states must satisfy. So keeping that aside, so I'm going to just use this cost function and continue with that. At the end, I'm going to comment on what happens if you generalize to other possible cost functions. So from this definition, we can also find the first law of complexity, that is considering small variations of the sources. And at this point, we arrive to this first law. This is just a purely boundary statement. There is no gravity so far in this equation. Okay, so next, we're gonna pick. So this definition that I gave you works for arbitrary deformations, delta 1 and delta 2. But in this paper by Bellin and company, they show that there is a special class of deformations such that the metric, it turns out to be proportional to the symplectic 2 form in such a way that the first law now yields change in complexity is equal to the symplectic form evaluated at this deformation, and this the second deformation is arbitrary. This is quite crucial because next we are going to use an equivalence between boundary and bulk symplectic forms. Using the ADS-CFT dictionary, we can see that what is the so-called Kähler potential, this log of lambda lambda, is nothing but the on-shell Euclidean action. And using the definition that I gave you for the symplectic form, this antisymmetric variation, we can then relate the boundary symplectic form to the bulk symplectic form. So the full integral is the symplectic form. This omega is what is called symplectic current. And one key point is that whenever the bulk is on shell, this symplectic current is closed, and we can pull the data to any other surface that is homologous to this surface, red surface. This is nice because then we can evaluate this first law at any other surface that is inside in the bulk, sigma. And essentially what this shows is the equivalence between boundary and bulk symplectic forms whenever the bulk is on shell, right? So on shell, I mean that it satisfies the equations of motion. Okay, so I told you that there is a special type of deformations that give you this first law. Assuming, so if we assume that this deformation is on shell, that means that applied to the equations of motion gives me 0. This identity gives you this identity. Then we can show that the first law of complexity, if we use this Stokes theorem and we pull the data to the bulk, it gives, the change in complexity is given by the bulk symplectic form evaluated at some surface sigma. Now, I need to tell you a little bit about this special deformation. This deformation is what in this paper they dubbed as the New York deformation. It satisfies some properties that are easy to understand in the ADM formalism. So this H and pi are just the metric, transverse metric, and the momentum. H bar is the traceless part of the metric. And using this deformation into this first law, then one can show that under this deformation, the bulk symplectic form gives you the variation of the volume of the slice sigma. So this is nice because this resembles the complexity volume conjecture. Although so far we have made some assumptions, and the assumption is that this deformation is on shell. That's something that we need to check a posteriori. And to be on shell, all the constraints of general relativity must be satisfied. In particular, the Hamiltonian constraint gives us that this equation here, this must be zero identically on shell. And that means that in order to this deformation to be on shell, the surface that I'm evaluating this on should be such that it has K extrinsic curvature 0. Right? So putting all together, what I'm arguing here is that the first law gives you the change in complexity is equal to the volume of not any particular any slice, but a slice that is maximal with K equals 0. So this is exactly CV, although this cannot be interpreted as a proof of CV. The reason is that here we are only referring to variations of complexity and not the complexity itself. Okay. Okay. So we move forward. So far I have shown you this trinity of complexity, where we have a triangle of relations. So in this corner, we have the change in complexity in the boundary. Assuming the boundary first law, then that is equivalent to the boundary symplectic form. And assuming that the bulk is on shell, we can relate this boundary symplectic form to the change in volume of some particular slice. Putting this together, we see that this is consistent with complexity equals volume conjecture. And this is essentially, so far, I'm summarizing the work of Belin et al. Okay, so put it just to sum up, what they did is to assume these two sides and show that the third leg is satisfied. Our work then makes a small twist to this triangle. So what we did is to assume the boundary first law and assume the bulk CV, and then show that as a result of these two assumptions, we can derive the third one, that is the linearized equations of motion in the bulk. Okay, so we assume these two. This is the boundary first law. We assume CV that gives this relation, and putting this together, we were able to show that the linearized equations are satisfied. So this is kind of the summary of our work. The proof follows from two steps. The first step is to essentially use Stokes' theorem in the bulk. So I'm integrating the symplectic current over this lower hemisphere. And then using Stokes' theorem, I can relate that to a part that is evaluated on the red surface. This is the boundary symplectic form. And a part that is evaluated at this blue surface that is related to the volume of that slice. So far, I'm not assuming that the bulk is on shell, so this might be 0 or this might not be 0. Next, so that I can do in general, and then what I'm assuming is the boundary first law and CV in the bulk. Then from this, for this integral, if I assume this, then this right-hand side vanishes because these two are equal to each other. And then we get this equation kind of integrated. Some comments about this is that for this deformation, this delta y, so this delta y E mu is 0 because essentially the New York deformation over the vacuum, for a small deformation over the vacuum, is just a large d field. So this is 0. Second, this part is generally non-zero. So this is the part that it must be 0. There is a caveat here. I'm just omitting some of the steps, but we obtain this equation only projected to a slice sigma. An extra step that I'm just mentioning here as a point is that we can do this for arbitrary slices sigma that give Lorentzian data. And we can repeat this to different slices that intersect a single point to obtain not only one component of these equations, but all of the components. And just in summary, then assuming these two things, then we are able to obtain the last part. Okay. So this is kind of the summary again, showing this triangle. We assume these two sides of the triangle, and we are able to prove the third one. This shows that at least in this context, linearized equations indeed emerge from this first law of complexity. And the idea is that this might hold for perturbations of, we show it for the perturbations around ADS, but it might hold for perturbations over, linear perturbations over general states. The idea holds true. The one caveat is that the explicit form of the deformation is only known around the vacuum ADS. So, okay, that's kind of the idea. In Einstein gravity, we can then proceed to modify some of the legs. The first thing that we tried is to keep the boundary first law as it is, and modify the complexity volume to account for other theories of gravity. So the first equation, we're keeping as it is. The second, now we're going to assume that this is proportional to another quantity that is can be interpreted as a generalized volume, that is W. There are some proposals for what this generalized volume is in higher curvature gravities. The first one by Pablo Bueno and collaborators. They derived this equation using the first law of causal diamonds in ADS. This is, in a sense, is something that resembles the Wald entropy, but now this applies for volume instead of area. There is a second work that builds up on this conjecture by Juan Hernandez and Rob Myers and other people. Although they went through a different path, they were using so-called double holography. And in their setting, they show that complexity is indeed given by this generalized volume, but crucially, they show that there is some extra terms proportional to extrinsic curvature that did not show up in this calculation around pure ADS. So this is more general, and this is analogous to this Kamsdon formula for holographic entanglement entropy. As some of you know, when you compute entanglement entropy in higher curvature gravities, it's not only the Wald term, but there are some anomaly terms that arises in that context. So this is analogous to that formula. In our context, however, we are not going to care about these corrections because as the first people did, we are going to assume perturbations about pure ADS. And in that case, the maximal volume slices are going to still be given by k equals 0 slices. So the second term will be irrelevant. Again, so what we do is to assume these two equations, and the proof, the first part of the proof amounts to showing this equivalence. This is a lengthy calculation, so I'm not going to show here, but once you show this, the next steps are more or less straightforward. The first part is to check that the so-called New York deformations are also on shell. That step is different than normal GR because the constraints of higher order gravities are different than the constraints of general relativity. So in general, we will get a different constraint that require that the surfaces are not exactly k equals 0. That's in the general case. In our case, when we restrict to perturbations about vacuum ADAs, again, we can show that at leading order, the surfaces that we're interested in are k equals 0 slices. So we can kind of overcome this more general problem by focusing on perturbations around pure ADS. And again, just following the similar steps, we can just show that assuming these two equations, then we are able to derive the gravitational equations, including these higher curvature corrections. Next, we added quantum corrections. By quantum corrections, I mean 1 over n, semi-classical quantum corrections. And for that, we also need to modify the lower leg. We have to incorporate this correction in the complexity equals volume proposal. Contrary to the higher curvature corrections, there are no proposals, or there were no proposals at the point that we were doing our work. So, So our first task was to determine these quantum corrections. In general, this is difficult, but we were able to do it by restricting to a simple theory of gravity, where semi-classical back reaction is possible. So we restrict to two-dimensional dilaton gravity, the so-called JT gravity. The important part here is that the action can be given by a classical piece. This is the classical JT gravity. It has the curvature tensor, but is coupled to a scalar field. That is important because otherwise the theory would be topological. So that's what gives the dynamics in 2D. And this is the kind of the cosmological constant. What is important is that in 2D, if I add a set of C bulk fields, I can actually compute a quantum effective action, one loop effective action that is completely encapsulated by this Polyakov term. Yes?
In the previous slide, you have in the denominators on D minus 2.
Previous slide.
I mean, previous. In the volume W.
W?
Yeah, this one. This.
Yes.
It's no problem, this?
Yes. So this doesn't work in that case. I will come to that point. Yeah, so this works for higher curvature gravities, but that are of the form Einstein plus corrections. But the 2D theory that I'm considering here is not Einstein, no? It's this dilaton gravity. So it's different. I will come to that in the next slide. Yeah, so I was telling you that the important point is that semi-classical effects can be completely encapsulated by this effective action. This is the Polyakov term that results from integrating bulk quantum fields at one loop. And it's important that in 2D, this term is one loop exact. So by that, I mean that all the back reaction effects are completely encapsulated by this term. The reason is that in 2D, the only thing that matters is the conformal anomaly. And this is precisely the action that gives it the right conformal anomaly. So that's why 2D is very simple. Semi-classical 2D gravity is simple. So complexity in 2D, we expect that complexity is proportional to volume, but with some caveat. So the reason is that this theory is not just Einstein gravity, it's just a dilaton gravity. And that means that the volume is not only going to be really the volume, but it's gonna have this dilaton factor here. We can understand this if we think of JT gravity from a dimensional reduction of a near extremal charged black hole. This is what you get when you start from volume in higher dimensions and go to 2 dimensions. And you can also understand this from the fact that one expects C to grow with the number of degrees of freedom. That is the entropy. Yes, question?
Yes, sorry, one question. In this interpretation of complexity in terms of JT gravity, is there an understanding of how that works for the dual matrix model? So JT gravity has a very specific dual matrix model. Is there any interpretation of complexity in that dual version?
Yeah. There are some works by Julian Sonner, I think, that compute complexity purely using this matrix model. And they show that in some limit, it matches with CV. In some limit, like infinite temperature, something like that. Yeah, I'm not super familiar with that, but I know that those works exist.
Okay, thanks.
Okay. Yeah, so I was saying that it's natural that the complexity scales with the dilaton in this way, because we expect that in some limit, C grows with the number of degrees of freedom, that is the entropy, and phi naught, that is the topological term, gives the extremal part of the entropy, but phi is what gives the deviation from extremality. So in particular, the first works on complexity in JT, they only use the first part, but it was not only until some works earlier this year that they realized that you need to actually add this term, and this term is important. So the way that we proceeded was the following. So the bulk symplectic form in this theory, it has 2 parts. One that is gravitational, that comes from the JT part, and one that is associated to matter fields. So the first part was to look for deformations, delta y, such that the gravitational part of the symplectic form is proportional to this volume. So that's kind of a generalization of this New York deformation, but in the context of JT. And we were able to find it quite easily. But next, what we did is to implement this transformation to the contribution of the symplectic form that is due to the matter fields. Okay, so doing that, we arrived to this contribution from matter fields. So we found that the bulk symplectic form is given by change in volume. That's the classical part. But we have this quantum part, or semi-classical part, that turns out to be proportional to the stress tensor integrated over some part of the manifold. Okay, so we arrived to this generalized formula. This is very reminiscent to the quantum corrected formula of entanglement entropy of Faulkner, Lekowicz, and Maldacena, where instead instead of only having the area, you have a bulk entanglement part. But in this case, just by analogy with that formula, we interpret this second term as a bulk complexity contribution. That's just a contribution that is due to the bulk quantum fields. And it's worth pointing out that this is consistent with this more general formula that was put forward by Juan Hernandez, Rob Myers, and collaborators, where they just conjecture that in general, you need to have this generalized volume plus anomaly terms plus a contribution of bulk fields. And this is consistent with that proposal. So in a nutshell, after we derive this extra term, we show that by consistency, again, assuming the boundary first law and bulk first law, we were able to derive the semi-classical equations. Well, I wrote this in quotes because in JT, the Einstein's equations are a little bit different. But in spirit, this is what we showed, that gravitational equations in 2D follow from boundary first law and this bulk first law, including this quantum part. We can ask about maybe if it is possible to do something analogous in higher D, but the problem is that semi-classical back reaction is not solvable, it's not easy to solve in higher D. Instead, what we can do is to propose that the bulk correction is the same in higher D. And assuming that the first part is, for example, just the volume that you obtain in Einstein gravity, we are indeed able to show that if this holds true, then semi-classical Einstein's equation hold. So we cannot show that this is the correction, but we can show that it is consistent. Okay, so finally, this is a parenthesis. I want to tell you about an interpretation of this CV. This is a little bit disconnected of the previous slides, but it's nice to have an intuition of what these quantities are computing. So for this interpretation, using the CV formula, we can actually rewrite this in terms of instead of maximizing a maximal volume formula, we can minimize the flux of a divergenceless vector field B that is has some norm bound. This equivalence follows from the something that is borrowed from network theory that is called the mean flow Matscat theorem. And in a discretized sense, the integral lines of this vector field is what are called the Lorentzian threads. We can interpret this formula as computing the minimal number of these Lorentzian threads, which means that it's very analogous to what we do in field theory, that is minimizing the number of operations. So in this picture, what I'm doing is showing a tensor network, discretizing some slides, and showing a set of discretized threads that pierce through these tensors in these slides. And attached to these threads are the unitary operations. So in a sense, this reinterpretation of CV connects quite well with what we expect for the definition of complexity in the boundary theory. And finally, we can, using a map between D-1 forms and vector fields, we can map this bulk symplectic current with a canonical solution for this vector field that gives rise to the right amount of complexity, but also such that the closedness condition maps to the divergenceless of B. That means that the Einstein's equations are in fact encoded in this condition. Okay, so that was kind of parentheses about the interpretation. Let me just summarize what I told you about. So I have argued that in some particular sense of complexity using holography, we were able to derive space-time dynamics by mapping it to an optimization problem in the boundary theory. So we have this triangle of relations. By consistency, if two of them are true, then the third one follows. And we just make use of this in a particular sense where we use a particular notion of boundary complexity, and we use complexity volume conjecture in the bulk. But it's worth exploring modifying some of these legs. For example, we can explore what happens if we change the cost function in the boundary, or what happens if we consider other generalized notion of bulk complexity. So we can try to test how robust is this principle of deriving gravity from computation. We can also try to go a little bit beyond what we did, that is including nonlinear corrections, and trying to interpret these other proposals using these threads that I showed you about. And with this, I conclude. Yeah.